Complex numbers are just numbers with more than one part. Now, we can envisage complex numbers with any number of parts, but for this session we'll just focus on complex numbers with two parts. Let's just recap a few of the things that we know about the terminology regarding numbers which are not complex, that is, numbers with only a single part. Now, numbers which only have one part we can represent as points on a one-dimensional line, which we call the number line. The numbers 1, 2, 3, 4 and so on, the numbers that we use for counting, are referred to by mathematicians as the set of natural numbers. If we also include the number 0, then we have what they call the set of whole numbers. And if we include numbers which are less than 0, that is negative or minus numbers, then we have what are referred to as the set of integers. If we also include the fractional numbers between the integers, then we have what mathematicians refer to as the set of real numbers. So, just as we can represent numbers with one part as points on a one-dimensional line called the number line, so we can represent numbers with two parts as points on a two-dimensional plane, which we call the complex number plane. Now, we can call these two axes of the complex number plane anything that we like, but mathematicians call the horizontal axis, which corresponds to the number line representing real numbers, the real axis. And so, by the same kind of terminology, they refer to the second axis as the imaginary axis. It's a bad term really, because there's nothing imaginary about the quantities that we represent in engineering using complex numbers, but they're the terminologies that are used by mathematicians, so we'll stick with them for now. Now, just as we mark off the real axis in units 1, 2, 3, 4, so we mark off the imaginary axis in units of what we symbolize by the lowercase letter I. Actually, in electrical engineering we tend to use the lowercase letter j instead, because I in electrical engineering is reserved for representing electric current. So on the positive direction of the imaginary axis we have I, which is the same unit along as 1 unit on the real axis, and we have similarly I2, I3, I4. Now notice that to symbolize the fact that we're talking about imaginary numbers here, instead of representing 2 units of I as 2I, we represent it instead by putting the I before the number. So 2 units of I, the imaginary unit I, we refer to as I2, I3, I4 and so on. And similarly in the negative direction on the imaginary axis we have minus I, minus I2, minus I3, minus I4 and so on. If we have a number then which is entirely on the real axis, we call it a real number. And if we have a number which is on the imaginary axis, we call it an imaginary number. If we have a number which has an imaginary component and a real component, we call it a complex number. It neither lies right on the real axis nor right on the imaginary axis. So how do we write complex numbers? There are two standard forms that we use to represent complex numbers, the rectangular form and the polar form. Let's take a look at those two terminologies. So we have a real and an imaginary axis, and we have a complex number which we'll represent by the letter n. It has a real component, we'll symbolize by the value a, and it has an imaginary component symbolized by the letter b. So in rectangular form we simply write the value of that complex number n as a, the real component, plus I, b, where b is the imaginary component and I is the imaginary unit that we discussed a moment ago. So that is the rectangular form of representing a complex number. As we said before, if you're an electrical engineer you'll tend to see it as a plus jb. In this example the complex number n is 3 plus I2, meaning it has a real component of 3 units along the real axis and an imaginary component of 2 units. Let's look at the polar form. the same imaginary number, the same complex number, instead of writing it as a real component and an imaginary component, we can express it as a distance from the origin, r, and a phase angle measured in a counterclockwise direction relative to the real axis and symbolized by the Greek letter theta. So in polar form, that same complex number we would write as r angle theta, where this symbol here just represents the angle of the complex number. So that is the same complex number expressed in polar form. In this example, the value of n is about 3.6 angle 33.7 degrees. Now how do we get that value? Well, if you remember from Pythagoras' theorem on a right angle triangle, the value of r squared, if we make a right angle triangle by dropping a perpendicular from the value down to the real axis here, then we have r squared would equal 3 squared plus 2 squared. So r is equal to the square root of a squared plus b squared, which is the square root of 3 squared plus 2 squared, which is about 3.6. Similarly, the angle theta is tan to the minus 1 of b over a. From basic trigonometry, the distance b divided by the distance a is the tangent of the angle theta. So the angle theta is tan to the minus 1 of b over a, which is tan to the minus 1 of 2 over 3, which is about 33.7 degrees. So the value of n then we can express in terms of, we can express it as a polar in polar form, but writing the polar values in terms of the numbers in the rectangular form. That enables us to easily convert between the rectangular form and the polar form. So we know that n equals r angle theta, and we can replace r by the square root of a squared plus b squared, and we can replace the angle theta by tan to the minus 1 of b over a, enabling us to simply convert a complex number in rectangular form, taking the a and b value, into the same complex number expressed in polar form. Similarly, if we want to go the other way and convert from the polar form into the rectangular form, we can express the value, we can replace the value a by r cos theta. From simple trigonometry we know that the value, this distance here a, divided by r would be the cosine of angle theta, so a itself would be r multiplied by cos theta, and similarly b is r sine theta. So n, the complex number n, expressed in rectangular form, but replacing the rectangular values a and b with the parameters from the polar form r and theta, n is expressed as r cos theta plus I sine theta. What about adding and subtracting complex numbers? Well, all we need to do is take a complex number which has a value of a1 as its real component and a value of b1 as its imaginary component, and we're going to add to it another complex number which has a real component a2 and an imaginary component b2, and we can add them, n1 which is a1 plus ib1 and n2 which is a2 plus ib2, and all we need to do to add them is add the real components a1 and a2 and the imaginary components ib1 and ib2, so that n1 plus n2, the sum of the two complex numbers, has a real component of a1 plus b1 and an imaginary component of b1 plus b2. Similarly, we can subtract complex numbers and say that n1 minus n2 is the real components a1 minus a2 plus an imaginary component of I times b1 minus b2. What about multiplying complex numbers? Well, multiplying complex numbers and dividing complex numbers, it's best to do it with the numbers expressed in the polar form. For adding and subtracting complex numbers, it's most convenient to do that with the complex numbers expressed in the rectangular form, but to multiply and divide, we're going to find it's much easier to do it with the complex numbers expressed in the polar form. Let's first of all look at the actual formula that we use for multiplying complex numbers, and then we'll show how to derive it. So two complex numbers, complex number 1, which is r1 angle theta 1, and another complex number r2 angle theta 2. It turns out that the product of these two complex numbers is just given by r1 r2 angle theta 1 plus theta 2. So in other words, we multiply the magnitude of the complex numbers together, the r1 and the r2, and we add the phase angles. So let's derive that formula then. We'll take two complex numbers, complex number 1, which is n1, r1 angle theta 1, expressed in rectangular form but with the rectangular coordinates given in terms of the r1 and the theta 1. So it's r1 cos theta 1 plus I r1 sin theta 1. And another complex number n2, which is r2 angle theta 2, or in the rectangular format r2 cos theta 2 plus I r2 sin theta 2. Now we can multiply these in rectangular form by saying that the product of the two complex numbers is this one, n1, which is this bit here, look, multiplied by n2, which is this term here. So we're just going to bring that down here, and now we're just going to multiply out these brackets. So we have this term, r1 cos theta 1, multiplied by this term, r2 cos theta 2, so that gives us this one, look, we've just multiplied them out and brought the r1 and r2 separately, plus this term multiplied by this term, so that's I times r1 cos theta 1 times r2 sin theta 2, plus this term times this term, so that's I times r1 sin theta 1 times r2 cos theta 2, and then finally this term multiplied by this term, so that gives us I squared r1 r2 sin theta 1 sin theta 2, and that equals this term here. All we've done now is we're going to see later on that the imaginary unit I actually turns out to be the square root of minus 1. So I squared becomes minus 1. So we can replace plus I squared multiplied by this term simply by saying it's equal to minus this term. So there you see we've just replaced the plus I squared with a minus sign. And if we then collect together the imaginary components and the real components, and then take the r1 and r2 out of the brackets, so we've taken r1 r2 out of the brackets of all these terms, and we've rearranged it so that we've put the remaining real term together, this bit plus this bit becomes here and here, and then we've taken the I out of the brackets as we've collected together the imaginary terms, so it's I times this bit plus this bit. And then from basic trig there is a trigonometric identity which identifies that cos of two angles A plus B is equal to cos A cos B minus sin A sin B. So if we substitute A for theta 1 and B for theta 2, we can see that we can replace this term here simply by saying it's cos of theta 1 plus theta 2. And similarly, using a trig identity where sine of A plus B is cos A sin B plus sin A cos B, again if we substitute theta 1 for A and theta 2 for B, then we can replace that term as I multiplied by r1 r2 sine theta 1 plus theta 2. and that is the equivalent expression in rectangular form of a complex number which in polar form would be written as r1 r2 angle theta 1 plus theta 2. You see we've got the same terminology that we have here. We've got an r term multiplied by a cos of an angle plus I r2 times sine of an angle, and the angle is just the sum of the two individual angles. So that's proved the formula that we looked at in the previous slide. Okay, what about dividing complex numbers? Similarly, we have the formula, which is the complex number r1 theta 1 divided by the complex number r2 theta 2, and it turns out that the answer is we just divide the magnitudes, and this time we subtract the phase angles. So r1 angle theta 1 divided by r2 angle theta 2 is equal to r1 over r2 angle theta 1 minus theta 2. Let's again go ahead and derive that formula. So here we have our two complex numbers, n1, which is r1 angle theta 1, and writing it again in rectangular form, but putting the rectangular coordinates, the real part and the imaginary part, in terms of the polar parameters r and theta, and a second complex number written in the same way. We can divide these two numbers by writing the rectangular form of them as shown here. We've just taken n1 and n2 and divided them, and if we take the r1 out of the brackets on the top and the r2 out of the brackets on the bottom, we have this. Now we can multiply the top and bottom, the numerator and denominator of a fraction, by the same thing, and it doesn't change it. So what I want to do now is multiply the top and bottom of this equation by something called the complex conjugate of the complex number on the bottom. Now a complex conjugate of a complex number is simply the same complex number but with the sign of the imaginary part reversed. Now the good thing about that is that when you multiply a complex number by its complex conjugate, or even add it to its complex conjugate, then you get rid of the imaginary part, and that's going to be useful as we see. Let's multiply the top and the bottom of the equation by the complex conjugate of this denominator part. So we're multiplying the top and bottom by, instead of cos theta 2 I sine theta 2, we're going to multiply it by its complex conjugate, cos theta 2 minus I sine theta 2, and we're going to multiply the top by the same value. So multiplying that out on the top and the bottom, the top of the equation becomes cos theta 1 cos theta 2, so that's that term, and then this term cos theta 1 I sine theta 2, so that's minus I sine theta 2 cos theta 1. Then this term I sine theta 1 times this term, so that's I sine theta 1 cos theta 2, and this term I sine theta 1 I sine theta 2, that becomes minus, because it's plus times minus, minus I squared sine theta 1 sine theta 2. Okay, now let's multiply out the bottom of the equation. So we have cos theta 2 times cos theta 2, so that's cos squared theta 2, and then cos theta 2, cos theta 2 times I times minus I sine theta 2, so that's minus I sine theta 2 cos theta 2, and then plus this term times this term, so that's I sine theta 2 cos theta 2, and then that term plus I sine theta 2 multiplied by minus I sine theta 2 becomes minus I squared sine theta 2. Now in the same way that we said before that we can replace plus I squared by a minus sign, so we can replace minus I squared by a plus sign, because, well, first of all let's just cancel out on the bottom. You see that this term is equal to that term, so the minus I sine theta 2 cos theta 2 and the plus I sine theta 2 cos theta 2 can be cancelled out, and then we can replace these minus I squareds by a plus sign, so that gives us this term remaining on the bottom, cos squared theta 2, plus, because we've replaced that minus I squared by a plus, plus sine squared theta 2, and we've replaced that minus I squared on the top with a plus sign. There you see, we just replaced it by a plus sign. And we have a trigonometric identity. By the way, these trigonometric identities, I'm going to do a separate video on these, which I'll link in the description below when they're completed. But we'll find out that sine squared plus cos squared of an angle equals 1, so we can replace that term on the bottom by a 1, and all we're left with is this expression here. And if we collect together the real parts and the imaginary parts, so there's a real part that can stay here, and there's a real part, sine theta 1, sine theta 2, that can go there, and then the imaginary parts, which is this part here, we can take the I outside of the brackets, and we've got I sine theta 1 cos theta 1 plus sine theta 2 cos theta 1. And back to our trig identities, where we can say that cos of A minus B is cos A cos B plus sine A sine B, and substitute A for theta 1 and B for theta 2 allows us to write that as R1 over R2 times cos theta 1 minus theta 2. And with this identity, sine A minus B is cos A sine B minus sine A cos B, so we can replace that term by R1 over R2, bring it in from here, and that becomes sine theta 1 minus theta 2, and that is the rectangular format of a number which in polar form would be expressed as R1 over R2 angle theta 1 minus theta 2. So you can see that we have just proved the formula for dividing complex numbers that we showed on the previous slide. How about square roots or other roots of complex numbers? Well, from what we know from earlier, we know that if we multiply two complex numbers R1 theta 1 by R2 theta 2, then the answer is R1 R2 multiplying the magnitudes together and adding the phase angles. So it follows that if we multiply a number by itself, written in polar form as R angle theta, if we multiply it by itself, in other words square it, we end up with R squared angle 2 theta. Just adding theta plus theta is 2 theta. So if we want to go the other way and take the square root, then we can see that the square root of the square root of a complex number expressed in polar form, R angle theta, would simply be the square root of the magnitude with the angle theta over 2. And similarly, the cubed root of a complex number R angle theta would be the cubed root of R of the magnitude with the angle theta over 3. And likewise the nth root would be the nth root of the magnitude R with the angle theta over n. What about the square root of minus 1, which we spoke about earlier? Let's use the information that we know, that we've learned about how we take how we divide numbers by themselves. How we divide complex numbers. We can express the number minus 1 as in polar terms as having a magnitude equal to 1 and a phase angle of 180 degrees. So, as we've mentioned, that if we want to take the square root of a complex number, we can simply take the square root of the magnitude and divide by 2 the phase angle. So the square root of a number R angle theta would be the square root of the magnitude, and the angle would be theta over 2. So let's substitute in the value of the number we want the square root of, minus 1, and we can say that the square root of minus 1, which is the square root of 1 angle 180 degrees would be the square root of the magnitude, which is 1, and the angle of 180 degrees over 2, which would be 90 degrees, which is actually I. So a magnitude of 1 and an angle of 90 degrees. So the square root of minus 1 is I. Actually, the square root of minus 1 is plus or minus I, because we can imagine another complex number, another imaginary number actually, with a magnitude of r and a phase angle of 270 degrees. If we do the same thing with that to take its square root, we would see that the magnitude of the answer would again be 1, but the phase angle, if we multiply that by itself, would be 270 degrees plus another 270 degrees, which would get us back to minus 1. What about the square root of I then? We can do the same thing. We can express I as 1, magnitude of 1, and an angle of 90 degrees. And as we did before, we can say the square root of our complex number would be the square root of the magnitude with the angle of the phase angle of the number we want the square root of divided by 2. So the answer would be square root of the magnitude 1 with the angle of 45 degrees. So that expression, that value there, that complex number there, with a magnitude of 1 and an angle of 45 degrees, would have a real component of cos 45 degrees, which is 1 over root 2, and also a real component, also an imaginary component of 1 over root 2, which is sine of 45 degrees. So the answer to the square root of I would simply be the real component in rectangular form, 1 over root 2, plus the imaginary component I times 1 over root 2, or 1 plus I over root 2. What about the uses of complex numbers? We've seen how we manipulate them and how mathematicians like to use them, but what use do they have in real terms? Why use complex numbers? Why use numbers that have more than one part? Why not just use more than one number? Well, we use them to generally complex numbers with two parts. We use them to represent what we call vector quantities, which are quantities that have more than one component, like a magnitude, a size, and a direction. For example, let's suppose that we are talking about movements, displacements. We might travel 5 miles in an easterly direction and then another 10 miles in a southwesterly direction. Rather than expressing distance and direction as two separate quantities, if we express them as a single quantity, which have magnitude and direction, then we can show them as complex numbers, and it makes it very easy for us to add them. So for example, in this example here, the resulting movement would be a distance travelled by adding the easterly components and the south components. Let's take a look at forces on an aircraft. An aircraft will have weight, which will be a force in a downward direction, and as the engines power the aircraft, it will have a force in a forward direction, which we'll call the thrust. It will also, because of air resistance, have a drag, which will hopefully be less than the thrust, so that the resultant movement in the horizontal direction will be forward. And as the aircraft starts to move forward, the wings will produce an upward force of lift, which will be greater than the force of gravity, its weight, downwards. So the resultant force will be a force in the forward and upward direction. Let's take a look at a vector quantity which has a magnitude and a phase angle rather than a magnitude and a direction. Let's look first of all at electrical resistance. Now, in electrical resistance, the resistance is expressed as the voltage divided by the current, and the current and the voltage in a resistive component will be exactly in phase. So if we determine the resistance as dividing the voltage by the current, we have the voltage waveform, which for a sinusoidal voltage will be V sine omega t, where the lowercase Greek letter omega is the angular frequency of the waveform, divided by the current. So V0 and I0 are the maximum voltage and the maximum current respectively, and you can see that if we divide the one by the other, we just get V over I. So because voltage and current are in phase, the resistance is a real number. However, if we look at a capacitor, in a capacitor the current waveform leads the voltage waveform by 90 degrees or pi over 2 radians. So we can, if we represent again the voltage waveform as V0 sine omega t, then the current waveform is I0 sine omega t plus pi over 2, because the current waveform leads, it's 90 degrees or pi over 2 radians ahead of the voltage waveform. Now, reactance is an electrical term which is similar to resistance, but it's for a capacitor or inductor, and the reactance, usually symbolized by the letter X, the capacitive reactance X sub C, is the voltage waveform over the current waveform, and that is V0 sine omega t divided by I sine omega t plus pi over 2. Now, because the current leads the voltage by 90 degrees or pi over 2 radians, the capacitive reactance is a negative imaginary number, whereas resistance is expressed as a positive number. The resistance is expressed as a real number on the complex number plane. Reactance can be expressed as a negative imaginary number. Remember that when we divide complex numbers, we subtract the phase angles. So V divided by I gives us a result with the phase angle of the voltage waveform, which has an angle of sine omega t, and the current waveform, which has an angle of sine omega t plus pi over 2. So the resulting phase angle is minus pi over 2, or minus 90 degrees. And because it has a negative phase angle, that puts it on the negative side of the imaginary axis. Let's have a look now at inductive reactance. In an inductor, the current waveform lags the voltage waveform, and again the reactance, this time which we represent as X sub L for inductance, inductive reactance, is the voltage waveform over the current, which is V0 sine omega t divided by I0 sine omega t minus pi over 2. And as we said, because the current lags the voltage by 90 degrees, the inductive reactance is a positive imaginary number. Remember, as we said before, that when we divide complex numbers we subtract the phase angles. So we're dividing V by I, so we're subtracting the phase angle of I from the phase angle of V. So we have sine omega t, which has this phase angle, minus sine omega t minus pi over 2. So the minus becomes a plus, and we have a phase angle of plus pi over 2, or plus 90 degrees. So that's going to be on the positive side of the imaginary axis. So real devices and circuits will have a voltage current relationship which will be somewhere between plus 90 degrees and minus 90 degrees. And we talk about the electrical impedance of a device or of a system as a combination of resistance and reactance, and it can be represented as a complex number, but the real part will always be positive. So if we look at our complex number plane, any impedance which is purely on the real axis, the positive real axis, will be resistive. Anything which is purely on the imaginary axis in the positive direction, in the negative direction, will be a pure capacitance, and anything which is somewhere down here will be capacitive but might have a combined resistive and capacitive component, but overall capacitive if it's in the negative imaginary part. and likewise anything which has an impedance which has a positive imaginary component will be inductive. The phase angle of the impedance, which is often called the power factor, actually the power factor is the cosine of the phase angle, will be, so a purely resistive load will have a power factor of 1. I think that's getting a little bit too much now for the basic introduction to complex numbers, so we'll call it a day. Thank you very much.